Hi again and welcome to this video lecture on neural networks. I am sure you have heard a lot about them here and there, like being magic bullet and doing so many things as the basis of deep learning and several uh, other variations of deep learning as the one of the most accurate, well-behaved learning algorithms. Neural networks were a major area of research both in neuroscience and computer science until 1969, when they were killed off by two MIT mathematicians. And then the technique came back in 1980s and then fell again into eclipse in the first decades of our new century. And then uh, returned like a gangbuster in the second, fueled largely by the increased processing power of graphic chips. Neural nets are a means of doing machine learning in which computer learns to perform some tasks by analyzing training examples, and usually these examples have been hand labeled in apps as well. Advanced. Yeah. First of all, you already know what a neural network is, and you probably even know how to build such a model. Uh, it is somewhat a logistic regression, yeah. As a matter of fact, the logistic regression model, or rather its generalization for multi-class classification called the softmax regression model, is a standard unit in a neural network. If you understood linear regression, logistic regression, and gradient descent, understanding neural networks shouldn't be a problem. A neural network is just like a regression or a support vector machine model, and the mathematical function is y is equal to f of n of x, and the function fnn has a particular form. It's a nested function, and you have probably already heard of network layers. So if we have a three-layer neural network that returns a scalar, fnn will look something like that. Y is equal f3 of f2 of f1 of x. And in this equation, f1 and f2 are vector functions of the following form. Fl of z is equal to gl of w l of z plus bl, and you see the linear function that we have used before. The function is called, GL is called the activation function. It is a fixed, usually nonlinear function chosen by the data scientist before the learning is started. And the parameters WL, which is a matrix, and BL, which is a vector for each layer, are learned using the familiar gradient descent by optimizing depending on the task. And if you compare this equation with logistic regression, where you replace GL by the sigmoid function, and then you see that there is no difference. The function f3 is a scalar function for the regression task, but it can also be a vector function depending on the problem. To make it more concrete, let's consider one architecture of neural network called multi-layer perceptron, which is often referred to a vanilla neural network. We have a closer look now at one particular configuration of neural network that is called feed-forward neural networks, and more specifically the architecture called multi-layer perceptron. As you see here, let's consider that our multi-layer perceptron has three layers. Our networks take a feature vector as the input, and then there's also a vector as the output. And this feed-forward neural network can be a regression or a classification depending on the activation function using the third output layer. The neural network is represented graphically as a connected combination of units logically organized into one or more layers, and each unit is circles. Could be represented by circle or rectangle. Here is a single, and the inbound arrow represents an output unit and indicates where this input came from, and the outbound arrow indicates the output of the unit. So you see the logic behind at least the picture is quite simple. And the output of each unit is the result of a mathematical operation written inside that circle. Circles, the units don't do much really with the input, they just send their input to the output after doing something on them. And as you can see here, in multi-layer perceptron, all outputs of one layer are connected to each input of the succeeding layer. This is the architecture that we call fully connected. A neural network can contain fully connected layers, and these are the layers whose units receive as input the outputs of each of the units of the previous layer. Basically, everything is connected to everything. If we want to solve a regression or classification problem discussed before, the last layer of the neural network usually contains only one unit, and the activation function of the last unit is linear. If it is linear, then the neural network is a regression model. If it is a logistic function, then the neural network is a binary classification model. And the data scientist could choose any mathematical function, assuming that it is differentiable. And this is important because it is for gradient descent we needed to be able to find the values of the parameters w and b. The primary purpose of having nonlinear components in the function f and n is to allow the neural network to approximate nonlinear functions. Without nonlinearities, the f and n would be linear, and then no matter how many layers it has. And the reason is that WL plus BL is a linear function, and the linear function of a linear function is also linear. And popular choices, and this is probably what is important you take from this slide, is that there are some popular choices of activation function, logistic regression, tanh or ReLU, and tanh is a hyperbolic tangent function similar to logistic function, but ranging from -1 to 1, and it doesn't really reach -1 and 1. And ReLU is rectified linear unit function, which equals to 0 when its input z is negative and to z other phi's. So again, the thing probably you need to take from here that these are two important activation function. One is linear, the other one is similar to the logistic activation function. Okay. To recap and say it in less technical terms, specifically, feed-forward neural network contains 3 types of layers of units. At the start of the neural network is an input layer where each unit contains an observation's value for a single feature. For example, if an observation has 100 features, the input layer has 100 nodes. At the end of the neural network is the output layer, which transforms the output of hidden layers into values that are useful for hands in task. Tasks in hand. For example, if our goal was a binary classification, we could use an output layer with a single unit that uses a sigmoid function to scale its own output between 0 and 1, representing a predicted class probability. Between the input and output layers are the so-called hidden layers. Well, I mean, they're not hidden, but they are just, you see them, but they are called hidden layers. And these hidden layers successively transform the feature value from input layer to something that, once processed by the output layer, resembles a target class. if neural network has many hidden layers, like 10, 100,000, then we consider them deep, and the application is called deep learning. So let me say it once again. A feed-forward neural network, input layer, output layer, and in between we have hidden layers. The number of units, these circles, in the input layer is equal to the number of observations we have had. So if we have a feature vector with 10 different features, then there are 10 circles in the input layer. And then whatever happens in between, this input is processed to get to the output layer, and depending on what we want to output, it is regression classification, then either we get a probability of belonging to different classes, or we get a continuous value for the regression. So the thing that happens inside is quite complicated, but the architecture is not: input, hidden layer, output. Neural networks are typically created with all parameters initialized as small random values from a Gaussian or a normal uniform. Once an observation, or more often a set number of observation, that is we call the batch, is fed through the network. So let's stop here. We basically feed to the network batches of observations, and you're going to see that in the practice part as well. So when the batch of observation is fed through the network, the outputted value is compared with the observations true value using a loss function. So the output is compared with the actual value based on a loss function, and this is called forward propagation. And next, an algorithm goes backward through the network, identifying how much each parameter contributed to the error between the predicted and true value. And that is a process called backpropagation. At each parameter, the optimization algorithm determines how much each weight should be adjusted to improve the output. So I stopped once again here. What happens is that we feed a batch of input to the network. It just goes forward propagation, gets to the output layer, we get something, we compare the result with the actual values. So based on the loss function, we get a value telling us how much error we have, how good or bad is that. Then we kind of backtrack the whole thing. We get back and see what are the units, what are the connections that made this error value larger, and if we can fix it in a sense to make it smaller. So this is the whole idea how a neural network: forward propagation, back propagation. And this is how neural network learns, by repeating this process of forward propagation and back propagation for each observation in the training data multiple times. So each time all observations have been sent through the network, we call that epoch. So epoch is basically when all the batches have gone through the neural network once. And training typically consists of multiple epochs. So the more you run it, you potentially could get a better update on the parameters. And a popular Python library to build this type of model is Keras, and that is used for building, training, and evaluating a variety of neural network. And Keras is a high-level library. Underneath, it uses TensorFlow and Theano sometimes as its engine. And the advantage of using Keras, and you're going to see how we use that in practice, is that we can focus on network design and training, and leaving the specifics of the tensor operations to the other libraries. Neural networks created using Keras can be trained using both CPUs on your laptop and GPUs on a specialized deep learning computer. In the real world, with real data, it's highly advisable to train neural networks using GPUs. However, for the sake of learning, all neural networks could be simple and sample and small, so that you can just try them on your laptop for a few minutes. But just be aware that when we have larger networks and more training data, training using CPU is significantly slower than training on GPU. Okay, So enough with talking about theory. Let's get hand dirty with a bit of practice. We're going to try a bit of coding for neural networks. So see you on the video on hands-on practice.